Okay, we're going to look at an example here of describing some of the characteristics or properties of a function. And for this problem, I've selected a pretty interesting looking function. I've got a graph here, and I labeled some points on the x and y axis just to be clear that the scale is 1 unit on both of the axes, but I labeled a couple of x coordinates that are going to be relevant to answering these questions. So first of all, let's look at this. On what open intervals is the function increasing, decreasing, and constant? Okay, and each one of those is a separate behavior, so we'll talk about what each of those mean real quickly, and then we'll describe where they're occurring. So increasing behavior, very easy. It's when a function's traveling up from left to right. Decreasing behavior is when a function is traveling down from left to right. And constant behavior, we don't see that one as much in some of the functions we're going to graph later, but constant behavior is where a function is just traveling horizontal. It's not going up or down from left to right. So in this example, let's start with increasing. If you look at this graph from left to right, it's never increasing. It's never going up from left to right. Okay, we read graphs often like we read books. It's read sentences in English, I guess, from left to right. So this function's never increasing. So as far as the answer, where is it increasing, or on what intervals is it increasing? None. There are no intervals. Now decreasing, right away, this function is decreasing. In fact, you can see right away it's decreasing on two separate intervals. It's decreasing over here, and then later on it decreases again. Now the biggest issue I think people have with this is just stating where it's decreasing. What we're looking for are open intervals on the x-axis. Okay, so based on what I see here, that from the far left side on the x-axis, way over here, when x is negative infinity, okay, the graph continues to move far to the left. We can see that based on that arrow on the left side. So it looks like from the very far left, as I move to the right, the graph is decreasing. And it stops decreasing when x is negative 3. So the first interval of decrease is from negative infinity to negative 3. Okay, because all along here on the x-axis, all along here, okay, the function's going down from left to right, but it stops that behavior at negative 3. And again, you might see that it's decreasing later on, just to the right of 2. Okay, so as I look to the right of 2 on the x-axis, it's going down again. So that's a second interval of decrease. It's decreasing from when x is 2 on to the right forever and ever and ever. So we say 2 comma infinity in parentheses. Now notice I don't include negative 3. I'm not putting a bracket here, just like I'm not putting a bracket with 2. Okay, why is that? Well, basically we don't include endpoints for these behaviors because at that point it's not really decreasing. Increasing, decreasing, all of those behaviors you observe as you move from left to right. So we don't really ever include endpoints with those behaviors. You could say maybe decreasing at negative 3, but another way to look at it would be right here at negative 3. It stops decreasing and it starts doing something else as we look to the right side. So notice we always want open intervals. That just means intervals not including the endpoints. So as we get to constant behavior, this function is constant. It's constant from negative 3 to 2. As we look at the graph between those two values, we don't see it move up or down. So that would be one interval of constant behavior. Okay, and again, not including those endpoints because the graph's not constant at those endpoints. It's sort of changing behaviors. Okay, so 3 basic concepts are kind of related. Some functions will have one interval of increase, one interval of decrease, 2 intervals of increase, 1 interval of constant. Really just about everything's possible depending on the function. And notice that, right at 2 and negative 3, again, we're not assigning any behavior to those 2 points. It's just the intervals to the left and right and between where the changes occur. Okay. Now let's go to kind of a slightly different question, but also something we like to be able to read from the graph of a function: the domain and the range. Okay, so let's start with the domain. The domain refers to all of the numbers which appear as x-coordinates on the graph. Now this takes a little while to get good at, or maybe to kind of get the gist of, but after you've done it a couple of times, it turns out to be pretty quick to do. If you have a well-drawn graph, you can find the domain really quickly. So for this function, the domain is going to be all real numbers. negative infinity to infinity. Okay, why is that? Well, it's because if you look from left to right, you can kind of make a little test for yourself to try passing through each point. If I pick a number like right here, that's -5. Is that number in the domain? Yeah, it is, because if I go up, I hit the graph. Sorry, just erase the graph a little bit there. If I go up, I hit the graph. So -5 would have to be an x-coordinate on the graph somewhere. Okay. Now, similarly, if I pick a point over here, say when x is 1, and I go up, I hit the graph again there. So 1 would be in the domain. Okay. Well, if you keep running this test through all the different points from left to right, you see that there isn't any point on the x-axis that won't be in the domain. Even, for example, when x is 2, if I move up from 2, I hit the graph. So on the x-axis, if you can pick a point and move up or down and hit the graph, that point is in the domain. And since every number appears to be in the domain, and again we're assuming that the graph continues to move in those two directions, we're going to say the domain is negative infinity to infinity. Okay. Now, range is very similar. The range of a function is the set of all y values on the graph. So what we do here is we kind of scan the y-axis from bottom to top and ask ourselves the same kind of question. What numbers are y-coordinates on this graph? Well, if you just pick one like -2, yeah, that's a y-coordinate, because if I move to the right, I hit the graph. +5, for example, if you look at 5 on the graph, on the y-axis right about here, if I move to the left, I'll hit the graph. So any number that's on the y-axis that gives us a y-coordinate somewhere on the graph is in the range. So when you look at this graph, you'll see that just about every number possible on the y-axis is in the range, except for some small little interval in here. Okay. When x is between 3 and 4, we don't ever get a point on the graph with that y-coordinate. Okay, I'm sorry, when y is between 3 and 4. So those numbers are not in the range. Okay. So in this problem, the range is going to be every number less than or equal to 3, those are all y-coordinates on the graph, and every number bigger than or equal to 4, okay, because even 4 itself is on the graph as a y-coordinate. Okay. So for the range, in this case, the range should be from -infinity to 3, and then from 4 to infinity. And notice we put brackets on 3 and 4, and the reason for that, again, it has to do with this particular graph. There are no y-coordinates of 3.1 or 3.9 or anything like that, but 3 is a y-coordinate. I see a solid dot to the right of y equals 3, so that is a y-coordinate on the graph. And similar for 4. If I look to the left of that y-coordinate, I hit the graph again. So that's also in the range. So that's also in the range. Okay. Now, one thing that's worth mentioning here real quick before we finish, notice that we put that U sign, that union symbol, between these two intervals. The reason we do that is the range of a function, we consider it one set. It might be 2 or 3 or 4 intervals, but together it makes one set of numbers. So typically when we have a set of several intervals, we put the union symbol between them. It kind of looks like a U without a tail. But when we're just listing intervals, like intervals where a certain behavior occurs, we just typically separate them by commas. So that's something that if you're working in my math lab, it might be kind of particular about. Intervals of decrease, notice here we just separated them by a comma because we see that behavior in 2 separate places. But the range of a function, together, it's all of the y-coordinates at once that we see on the graph. So put that union symbol there to indicate it's a single set. Okay, well, that's it.